You begin exactly where you are. Perhaps you are lying down. Perhaps you are sitting quietly, your feet resting on the floor. Beneath you is the ground, firm, dependable, steady. It feels permanent. It feels finished. When you press your hand against the earth, or imagine the soil beneath a building, you sense something solid and unmoving. The ground feels like certainty. For most of your life, you have trusted this stillness. You walk without hesitation. You build homes, cities, roads. You sleep without wondering what moves below you. The earth seems calm, like a great stone table that has always existed and always will. But tonight, in this slow and gentle journey, you allow your imagination to soften that certainty. You begin to sense that the stillness is only a surface story. The outermost layer of the earth, the crust, is thin. Surprisingly thin. If the planet were the size of an apple, the crust would be no thicker than the apple's skin. Everything you know, mountains, oceans, forests, cities, rests upon this delicate outer layer. Beneath that thin skin, the planet is not cold and rigid. It is warm. It is dynamic. It is alive with motion so slow you rarely notice it. You picture the soil beneath you first. Dark grains. Tiny roots. Insects moving quietly. A few feet deeper, the soil gives way to solid rock. Layers of sandstone, granite, basalt, ancient materials formed under pressure and heat over millions of years. Even deeper, the temperature begins to rise. For every kilometer you travel downward, the Earth grows warmer by roughly 25 to 30 degrees Celsius. It is a slow increase, like descending into a bath that grows gradually hotter. You do not feel it from where you are, but the warmth is there, building with depth. This heat is not random. It has a story. Some of it is leftover energy from when the planet first formed, more than 4.5 billion years ago, when dust and rock collided and fused in a violent dance around the young sun. Those impacts generated enormous heat, and some of that ancient warmth still lingers deep inside. Some of the heat comes from radioactive elements, tiny unstable atoms within the Earth that slowly break apart. As they decay, they release energy. It is a quiet process, invisible and constant, like a slow internal fire that never quite goes out. So beneath your feet, there is warmth. Beneath that warmth, there is more. You imagine descending farther now, miles below the surface. The rock here does not behave the way rock behaves in your hand. Under immense pressure and high temperature, it becomes something softer, something that can bend over long periods of time. Not liquid exactly, but not rigid either. It flows slowly, patiently, like very thick honey over thousands or millions of years. The Earth is not a frozen statue. It is a slow-moving system. This movement is almost impossible to see in a single lifetime. But over deep time, continents drift. Mountains rise. Oceans open and close. The ground beneath you is part of a vast, slow choreography that has been unfolding for eons. And yet, from where you rest, everything feels calm. You begin to notice something comforting in that contrast. Stillness above. Motion below. The surface world, your world, feels steady because the movements underneath are slow and patient. The Earth does not rush. It does not hurry its processes. Heat rises gradually. Rock shifts millimeter by millimeter. Pressure builds grain by grain. Pressure. It is an interesting word. You feel it in your own life sometimes, expectations, responsibilities, time. But deep underground, pressure is something physical and immense. It is the weight of miles of rock pressing downward with unimaginable force. At just a few kilometers below the surface, the pressure is already thousands of times greater than the air pressing gently against your skin right now. Deeper still, it becomes almost beyond comprehension. And yet, the materials below endure it. Rock adapts to pressure. It compresses. It transforms. Minerals rearrange their internal structures. Under enough heat and force, solid stone can even begin to melt. You imagine that melting not as chaos, but as a quiet transition. Crystals loosen their grip on one another. Structures soften. Solid becomes fluid. What was rigid becomes mobile. All of this is happening beneath you. Not dramatically. Not violently. Simply steadily. The earth is breathing in its own way. Heat rises upward from the deep interior. Cooler material near the crust sinks slowly downward over long spans of time. This cycle, called convection, is like a slow simmer in a pot of thick soup. Warm material expands and rises. Cooler material contracts and sinks. You cannot hear it. You cannot feel it. But it continues. And because it continues, the surface you rest upon is never entirely at rest. It floats, in a sense, atop these deeper motions. The crust is broken into enormous pieces, though you cannot see the seams from where you are. These pieces drift slowly, carried by the currents beneath. Tonight, you do not need to know all their names. You simply feel the idea: the ground is not a single, unmoving slab. It is part of a layered, living system. There is something strangely soothing about this. The earth is active, yes. Warm, yes. Pressurized and powerful, yes. But it is also patient beyond imagination. Its movements unfold over millions of years. Its changes are measured not in minutes or hours, but in epochs. You are resting on a planet that has endured collisions from space, global ice ages, mass extinctions, and the slow rearrangement of entire continents. And still, tonight, it holds you gently. The ground beneath your feet feels quiet because the forces below move with immense restraint. Energy gathers slowly. Heat accumulates gradually. Pressure builds invisibly, layer upon layer. Nothing is wasted. Nothing is hurried. You begin to sense that what feels solid is actually a balance, a delicate equilibrium between heat rising from below and rock resisting from above. A conversation between fire and stone. And like any conversation, it continues even when you are not listening. As you rest here, breathing softly, the planet beneath you is also engaged in its own long breath. Warmth rising. Material shifting. Pressure forming deep in chambers you cannot see. You do not need to fear this motion. You are simply becoming aware of it. You continue downward. Not with your body, but with your imagination, gently descending through layers of rock, past the roots of mountains, beneath the quiet foundations of cities, slipping deeper into warmth. The light fades first. Then the sense of open space. The world becomes stone around you, dense, ancient, silent. Yet even here, there is change. The deeper you travel, the warmer it grows. Not suddenly, not violently. Just steadily. Patiently. The earth holds a hidden furnace. At about 30 kilometers below many continents, you pass through the crust and enter a region called the mantle. It is not a hollow chamber, not a cavern filled with fire. It is solid rock, and yet, under immense heat and pressure, that solid rock behaves differently than the stone you see at the surface. Here, temperatures climb beyond 1,000 degrees Celsius. Deeper still, they rise toward 3,000 degrees. It is a heat so great that if you could place a piece of surface granite here, it would begin to weaken, its minerals trembling at the atomic level. You imagine atoms as tiny dancers locked in formation. Heat is energy, and when energy increases, the dancers move more vigorously. They vibrate, twist, and strain against the bonds that hold them together. At the surface, rock feels eternal. Down here, it feels almost alive. Pressure is immense. Miles of rock press downward with relentless force. You might think that such pressure would prevent melting entirely. And often, it does. Pressure keeps rock solid even at very high temperatures. But the Earth is subtle. Melting does not require everything to turn liquid at once. It begins in small pockets, where conditions shift just enough. Perhaps the temperature rises slightly higher. Perhaps pressure decreases as rock slowly shifts upward. Perhaps water, carried down by sinking tectonic plates, lowers the melting point of surrounding stone. And in those moments, something remarkable happens. Solid rock begins to melt into magma. Magma is not just melted rock. It is a mixture of liquid minerals, suspended crystals, dissolved gases. It glows with stored heat. It moves slowly, like thick syrup, gathering in pockets and chambers deep below the crust. You imagine it as liquid thought beneath a stony mind. It does not rush. It does not roar. It forms gradually, accumulating in hidden reservoirs. Some magma cools and solidifies before ever rising far. Some lingers for thousands of years. Some begins a slow ascent toward the surface. This ascent is driven by buoyancy. When rock melts, it often becomes slightly less dense than the surrounding solid material. Like warm air rising through cooler air, magma can begin to rise through cracks and weaknesses in the crust. It is not a dramatic surge. It is more like a careful seep, a patient migration upward through fractures that open over time. You are witnessing a process that shapes continents. Deep below, convection currents continue their slow turning. Hotter mantle material rises. Cooler material sinks. This circulation transfers heat from the deep interior toward the surface. It is Earth's way of releasing the energy it has carried since its formation. And yet, the planet does not cool quickly. The mantle remains vast and hot. The core even deeper burns at temperatures comparable to the surface of the sun, though it shines with no visible light. You are far above that core now, resting in the upper mantle where partial melting begins. You sense how delicate the balance is. A slight change in temperature. A subtle shift in pressure. The presence of water lowering the melting threshold. These small variations create pockets of magma in specific regions, not everywhere at once. This is why volcanoes form where they do. Not randomly, but where conditions allow melting to occur. In some places, tectonic plates pull apart. As the crust stretches, pressure decreases slightly in the mantle below. This decompression allows rock to melt without additional heat. In other regions, one plate sinks beneath another, carrying water downward. That water reduces the melting temperature of mantle rock, encouraging magma to form. Each scenario is a quiet negotiation between heat and pressure. You begin to sense how pressure is not only a force that prevents melting, it is also a sculptor of where melting can happen. When pressure decreases just enough, melting begins. When pressure increases, melting halts. The Earth's deep furnace is not chaotic. It is responsive. Magma chambers, those reservoirs of molten material, are born from this balance. They gather slowly, fed by repeated injections of melt from below. Each new pulse of magma adds heat, adds volume, adds dissolved gases. Gases are important here. As rock melts, gases such as water vapor, carbon dioxide, and sulfur dioxide dissolve into the liquid. Under high pressure, they remain trapped within the magma, like carbonation dissolved in a sealed bottle. But as magma rises and pressure decreases, those gases begin to separate, forming bubbles. You can imagine it easily opening a bottle of sparkling water. The liquid is calm under pressure. But when the cap is removed, bubbles appear, expanding rapidly. Deep underground, this process unfolds slowly. Gas bubbles form within magma as it ascends. Their expansion increases internal pressure inside the molten rock. Pressure within pressure. The earth holds layers of force interacting with one another. Heat creates melt. Melt gathers. Gases dissolve and then expand. Surrounding rock resists. Cracks form. Pathways open. But still, everything remains largely unseen from the surface. You rest above it all, unaware of the slow transformations miles below. There is something profoundly gentle about this hidden activity. It is powerful, yes. Capable of shaping landscapes and altering climates. But it unfolds in silence for long stretches of time. Thousands of years may pass as magma accumulates quietly. Centuries may drift by while pressure builds grain by grain. The deep furnace does not hurry. You begin to feel how melting rock is not destruction, but transition. Solid becomes liquid. Rigid becomes fluid. Structure becomes possibility. In your own life, you have known moments when something rigid within you softens under warmth. Certainty melts into openness. Pressure transforms into movement. The earth mirrors this process on a grand scale. Down here, rock is not fixed forever. It responds to energy. It shifts when conditions change. It flows when given time. And as magma gathers in hidden chambers, buoyed by heat and stirred by convection, it carries with it the memory of the deep interior, the ancient warmth of a planet still cooling from its birth. You sense that this gathering is not random. It is preparation. Magma pooling beneath the crust is potential energy waiting patiently. It presses gently against the rock above. It warms its surroundings. It expands as gases slowly separate within it. The stage is being set not for immediate drama, but for something that requires both time and tension. And as you hover here in imagination, suspended between solid mantle and molten pockets of rising magma, you begin to understand that pressure is not an enemy of motion. It is its partner. Heat alone does not create transformation. Pressure alone does not either. Together, they shape the deep architecture of the planet. And somewhere above this hidden furnace, where immense slabs of crust drift slowly across the surface, their movements will soon begin to influence where this molten thaw can gather and rise. You rise gently now, back toward the surface. Not all the way to the open air, but to the fragile boundary between the deep furnace and the world you know. Here, the crust rests like a shell over the mantle, thin, fractured, and quietly in motion. It does not feel as though it moves. When you stand on the ground, it feels absolute. But the crust is not one unbroken piece. It is divided into enormous slabs called tectonic plates. These plates fit together like pieces of an ancient puzzle, though the seams are hidden beneath oceans and continents. You are standing on one of them now. They drift slowly across the surface of the mantle, carried by the steady convection currents below. The movement is almost impossible to notice, often just a few centimeters each year. About as fast as your fingernails grow. And yet, over millions of years, that small motion becomes immense. Oceans open. Mountains rise. Continents separate and reunite. You imagine looking down at the Earth from far above, watching time speed forward like a silent film. The continents shift like floating leaves on dark water. They draw closer. They pull apart. They rotate slightly, as though nudged by invisible hands. But there are no hands. Only heat, rising from below. Where plates move apart at divergent boundaries, something gentle and creative happens. The crust stretches and thins. Beneath it, pressure decreases slightly, just enough for mantle rock to melt. Magma rises to fill the gap, cooling into new crust. This is how ocean floors are born. At places like the Mid-Atlantic Ridge, new seafloor forms continuously, though you would never see it happening in real time. It is a patient widening, and underwater seems slowly stitching fresh rock into the planet's surface. Movement creates space. And space invites melting. But not all plate boundaries are so calm. Sometimes plates slide past one another horizontally. These are transform boundaries. The motion is sideways, grinding intense. Friction builds. The plates catch and hold, resisting motion until the accumulated stress becomes too great. Then, suddenly, they slip. An earthquake releases energy that has been stored for years, sometimes centuries. The ground shakes not because it is fragile, but because it is adjusting, redistributing pressure along the fault. Even this is part of the conversation. But perhaps the most dramatic exchanges occur where plates collide. You picture one plate meeting another head-on, neither willing to yield easily. If both are continental, thick and buoyant, they crumple upward instead of sinking. Over millions of years, this collision pushes mountains skyward. The Himalayas rise this way, still growing today as the Indian plate presses into the Eurasian plate. Stone folds like fabric under pressure. But when an oceanic plate meets a continental plate, something different occurs. The oceanic plate, denser and thinner, bends downward and sinks beneath the continent in a process called subduction. It descends into the mantle like a slow, relentless bow. As it sinks, it carries with it water trapped within minerals and sediments. That water lowers the melting point of the mantle rock above the descending plate. And once again, melting begins. Magma forms in arcs above subduction zones, often giving rise to chains of volcanoes along continental edges. Movement creates tension. Tension creates melting. Melting gathers into chambers. You begin to sense the pattern. The plates are not chaotic wanderers. They are participants in a slow dialogue driven by the heat beneath them. Convection currents in the mantle push and pull at their undersides. Gravity helps guide subducting plates downward. Ridge push and slab pull, subtle forces acting over vast spans of time, keep the motion continuous. It is a system of balance. But balance does not mean stillness. Imagine placing your palms together and pressing gently. You feel resistance. Increase the pressure slightly, and your muscles respond. Increase it more, and strain appears. The Earth experiences something similar at plate boundaries. Stress accumulates slowly where motion is resisted. Rock bends elastically at first, storing energy like a compressed spring. Over time, if the stress exceeds the strength of the rock, it fractures. And beneath some of these collision zones, magma chambers begin to form. Repeated injections of molten rock from the mantle gather in reservoirs within the crust. Each pulse adds heat. Each addition increases internal pressure. Surrounding rock is warmed, softened, sometimes partially melted. These chambers are not smooth spheres of glowing liquid. They are complex networks of melt pockets and crystal-rich mush zones. Some portions are fluid. Others are semi-solid. It is more like a slowly churning mixture than an open cavern. And yet, from the surface, nothing may appear unusual. You might see mountains. You might see forests. You might see cities. All the while, beneath, plates converge and separate. Pressure builds and releases. Magma gathers in places shaped by these immense tectonic conversations. You realize that the surface calm you experience each day is supported by motion that never truly stops. Even now, as you rest, your plate is drifting. Slowly. Patiently. The Atlantic Ocean widens by a few centimeters this year. The Pacific shrinks slightly along its edges. Continents inch toward futures that no single human lifetime will witness. This knowledge does not need to feel frightening. It can feel humbling. You are part of a moving planet. The ground beneath your home was once somewhere else entirely. Hundreds of millions of years ago, the continents were joined in a supercontinent called Pangaea. Before that, other configurations existed. The crust rearranges itself over geologic time like a breathing mosaic. And within this rearrangement, zones of weakness develop. Faults form. Subduction zones deepen. Rift valleys widen. These are the places where magma most often finds opportunity. The deep furnace sends up melt. Plate movements create pathways. Pressure accumulates in confined chambers. Gas dissolves within molten rock. You can almost feel the slow tightening of a system preparing itself, not in haste, not in panic, but through accumulation. Movement creates tension. Tension creates possibility. And in certain rare places, where conditions align over thousands of years, those magma chambers will grow far larger than ordinary volcanic systems. Not small peaks. Not isolated cones. But something vast beneath the crust, something capable of reshaping entire landscapes. As the plates continue their silent drift, pressing, sliding, sinking, and lifting, you begin to sense that one of these tectonic conversations is quietly building towards something much greater. You begin with a familiar image. A volcano rising like a cone against the sky. Slopes of dark rock. A summit crater. Perhaps a ribbon of smoke drifting upward. This is how stories often draw volcanoes: dramatic, visible, unmistakable. But now, gently, you let that image fade. Not all volcanoes rise as mountains. Some lie hidden beneath flat valleys. Beneath forests. Beneath lakes and wide open plains. From above, they may appear ordinary, almost peaceful. There is no towering peak to warn you. No obvious sign of what rests below. Instead, there is space. A vast, quiet space beneath the crust. A supervolcano does not begin with an eruption. It begins with accumulation. You return in your imagination to the deep furnace, to the mantle where rock partially melts under the right balance of heat and pressure. There, over long stretches of time, magma forms and rises. In most volcanic systems, this melt gathers in relatively small chambers within the crust. Enough to fuel eruptions that build mountains layer by layer. But sometimes, conditions allow for something far larger. Repeated pulses of magma rise from below, one after another, over tens of thousands of years. Each injection brings new heat into the crust. Each addition melts surrounding rock slightly, enlarging the reservoir. The chamber grows not in a single moment, but in increments, a slow expansion of molten thought beneath solid stone. You picture it like a lung slowly filling. Not in seconds, but in centuries. The crust above this chamber acts as a ceiling, strong, but not infinite in strength. Rock, even strong rock, responds to heat. As magma accumulates, it warms the surrounding crust. Minerals expand slightly. Cracks form and seal. The entire system becomes softer, more flexible. Yet still, it holds. A supervolcano is defined not by shape, but by scale. The magma chamber beneath it can span tens of kilometers across. It may contain hundreds or even thousands of cubic kilometers of partially molten material, though not all of it is liquid at once. Much of it exists as a crystal-rich mush, a mixture of solid and melt in delicate balance. It is not an empty cavern glowing with fire. It is more like a vast sponge of heated rock, threaded with molten pathways. You imagine standing on the surface above such a chamber. The land may rise gently into rolling hills. Forests grow. Rivers flow. Animals wander without knowledge of what rests far below. There may be hot springs or geysers, small reminders that heat is near the surface, but nothing that announces the full scale of what lies beneath. Supervolcanoes often form in places where tectonic conditions create sustained melting. Sometimes this happens above mantle plumes, columns of unusually hot material rising from deep within the mantle. These plumes deliver extra heat to the base of the crust. As the crust moves slowly over them, magma can accumulate in one region for extended periods. Other times, large magma bodies develop in continental collision zones or rift systems where the crust is already weakened. But regardless of location, the pattern is similar. Heat gathers. Magma intrudes. Chambers expand. And above them, the crust bends. You imagine the ceiling of the chamber slowly arching upward as molten material accumulates below. The land at the surface may rise by meters over centuries, so slowly that no single generation notices. It is a subtle swelling, measurable only with precise instruments. The crust stretches like fabric pulled gently from beneath. But rock is not fabric. It does not stretch indefinitely. It has limits. As magma continues to accumulate, gases dissolved within it begin to play a larger role. Water vapor, carbon dioxide, sulfur dioxide, these gases are trapped under immense pressure deep underground. As new magma enters the chamber, pressure increases further. It is like adding air to an already full balloon. The roof of the chamber feels this pressure. Microfractures form within the rock. Some seal with new mineral growth. Others remain as zones of weakness. Yet for long periods, nothing dramatic happens. This is important to understand. A supervolcano is not constantly on the edge of eruption. It may remain in a state of partial melt and internal motion for hundreds of thousands of years without producing a supereruption. The system breathes in smaller ways, minor intrusions, localized eruptions, hydrothermal activity releasing some heat and gas. These smaller releases act like sighs. They reduce pressure slightly. They maintain balance. But in rare cases, the chamber grows so large, and the internal pressure becomes so great, that the strength of the overlying crust is tested beyond recovery. You imagine the chamber reaching a threshold, not suddenly, but through gradual accumulation. Each new pulse of magma adds both volume and volatile gases. The crust above thins and fractures in subtle patterns. The structural integrity weakens. It is a slow negotiation between containment and expansion. If the balance tips, the consequences are immense. But before any eruption, there is a moment of tension. A vast body of magma pressing outward in all directions. Rock straining to hold its shape. Gases expanding within molten pathways. The chamber roof arching slightly, then slightly more. You feel this is a kind of geological inhale, a breath drawn over centuries. Supervolcanoes do not erupt frequently. The intervals between major events are often measured in hundreds of thousands of years. This rarity is part of what makes them so powerful. Energy accumulates for extraordinary spans of time before release. And when release does come, it is not a simple explosion from a cone-shaped mountain. Instead, the roof of the magma chamber may collapse inward as enormous volumes of material are expelled. The landscape above can sink into the emptied space below, forming a vast depression called a caldera. But that moment is not here yet. You remain in the time before, in the quiet era of gathering. The birth of a supervolcano is not a single event. It is a process of accumulation, warming, softening, and expansion. It is centuries of molten rock arriving in pulses. It is pressure building invisibly beneath forests and plains. From above, life continues without awareness. Seasons change. Rain falls. Snow gathers and melts. Beneath it all, a chamber grows. There is something strangely reflective in this image. So much of the world's most powerful change begins unseen. Energy gathers quietly. Conditions align slowly. What appears calm may hold vast potential beneath. You do not need to fear this knowledge. It is simply part of understanding the living planet beneath you. Tonight, you rest above crust that may or may not conceal such a chamber. Most places on Earth do not. Supervolcano systems are rare. But where they do exist, they represent one of the most immense expressions of internal planetary heat. And somewhere on this planet, beneath wide skies and wandering rivers, there is a place where a supervolcano once erupted and where heat still lingers today, quietly monitored, quietly breathing beneath the surface. You arrive in a place of open sky. Imagine standing in the wide valleys of Yellowstone National Park in the United States. Forests stretch toward distant ridges. Rivers wind through meadows. Bison move slowly across the grass, their breath visible in cool morning air. It feels peaceful here. The landscape does not resemble a volcano in the way you might expect. There is no sharp cone rising into the clouds. No blackened slopes or constant rumble of fire. Instead, there are rolling plateaus and broad basins, quiet lakes reflecting blue sky. And yet, beneath your feet, one of the most powerful volcanic systems on Earth rests. Yellowstone is a supervolcano. Not a mountain, but a caldera, a vast depression formed by enormous eruptions in the distant past. The caldera here spans roughly 70 kilometers long and 30 kilometers wide. So wide that if you stood inside it, you might not even realize you were within the remains of an ancient eruption. You were standing inside the memory of something immense. About 2.1 million years ago, Yellowstone experienced a colossal eruption. Ash spread across much of North America. Another major eruption followed about 1.3 million years ago. And the most recent supereruption occurred approximately 640,000 years ago. These numbers are almost impossible to feel. Hundreds of thousands of years. Time stretches gently when you think of it this way. Human history occupies only a small fraction of that span. Entire civilizations rise and fall in what is, to the Earth, a brief pause between breaths. After the last supereruption, the emptied magma chamber beneath Yellowstone caused the ground above to collapse inward. The land sank, forming the enormous caldera you stand in now. But Yellowstone did not fall silent. Smaller eruptions continued for tens of thousands of years. Lava flows filled parts of the caldera floor. Hydrothermal systems developed as groundwater interacted with heat still rising from below. This is why Yellowstone steams. You picture a geyser, perhaps Old Faithful, sending a column of hot water skyward in a rhythmic burst. These eruptions are not powered directly by magma reaching the surface, but by water heated deep underground. Rain and snowmelt seep into the ground, travel downward through cracks, and encounter hot rock heated by magma below. The water boils. Steam forms. Pressure builds within underground plumbing systems. And then, in a sudden release, the geyser erupts. It is like a small, harmless exhale from a much deeper source of warmth. Yellowstone contains more than 10,000 hydrothermal features: geysers, hot springs, mud pots, fumaroles. It is the largest concentration of such features on Earth. Each one is a reminder that heat remains beneath the surface. But heat alone does not mean eruption. Scientists study Yellowstone carefully. Not with alarm, but with attention. Seismometers are placed across the park to detect earthquakes too small for you to feel. Most of these quakes are tiny, small adjustments in the crust as it responds to shifting pressure. Yellowstone experiences thousands of minor earthquakes each year. They are usually harmless, part of the system's natural movement. Satellites orbit high above, measuring the ground's elevation with remarkable precision. Over years, scientists have observed parts of the caldera rising and falling by several centimeters. This uplift and subsidence reflect changes in magma and fluids beneath the surface. It is as if the land itself is breathing. Gas sensors monitor emissions from vents and hot springs. Carbon dioxide and sulfur dioxide seep upward from deep underground. Changes in these gases can offer clues about shifts in the magmatic system. You begin to understand that sleeping does not mean inactive. Yellowstone is not frozen in time. It is dynamic. Heat circulates. Magma exists beneath the crust in a complex system of reservoirs, some partially molten, some mostly solid. Recent research suggests that much of the magma beneath Yellowstone is not a vast ocean of liquid, but a crystal-rich mixture, molten in parts, solid in others. This matters. For a supereruption to occur, a significant portion of that magma would need to accumulate as eruptible melt. Current studies indicate that while Yellowstone remains active, there is no sign of an imminent supereruption. Imminent, in geological terms, means thousands to tens of thousands of years. The system is monitored precisely because understanding reduces fear. You imagine scientists walking quietly across steaming ground, setting up instruments, collecting samples. They are not waiting for disaster. They are listening, learning the rhythms of this immense geological heart. Yellowstone teaches patience. The eruptions that formed this caldera were separated by hundreds of thousands of years. Between them were long stretches of relative calm, punctuated by smaller lava flows and hydrothermal activity. Even now, the magma beneath Yellowstone is slowly cooling and crystallizing in places. New injections of melt may occur occasionally from deeper mantle sources. But the system evolves gradually. You stand beside a hot spring, watching colors ripple across its surface, blues and oranges created by heat-loving microorganisms. Life thrives here because of geothermal warmth. What was once destructive becomes generative. The earth does not hold only threat. It holds renewal. You feel the paradox gently settle within you. Yellowstone is both powerful and peaceful. Ancient and present. Dormant and alive. The word sleeping suggests something that could wake suddenly. But in geology, waking is rarely sudden. It is preceded by signals: increasing earthquakes, significant ground deformation, changes in gas emissions. The planet communicates before it transforms. And for now, Yellowstone communicates calm activity. Heat rises. Water circulates. Small quakes adjust the crust. Scientists observe and learn. You look across the wide sky above the caldera and realize that you are standing atop a system shaped by immense forces, yet currently resting in balance. The last supereruption occurred long before human memory. The probability of another in your lifetime is extremely low. Time stretches again, soothing and vast. You do not stand on the edge of catastrophe. You stand on ancient ground that continues its slow evolution. And beneath this immense park, beneath forests, rivers, geysers, and wildlife, magma still lingers, warm and patient, reminding you that pressure does not always lead to immediate release. You remain beneath the surface. Not in fear, not in urgency, but in quiet observation. Yellowstone rests above its vast magmatic system, and yet nothing dramatic unfolds. Forests sway. Geysers pulse. Snow falls in winter and melts in spring. Life continues, unaware of the slow arithmetic happening below. This is where you begin to understand pressure. Pressure is rarely sudden at first. It is accumulation. A gathering. A steady addition of small changes over long spans of time. Deep underground, magma does not simply appear all at once. It arrives in pulses. Small injections from deeper mantle sources move upward into existing reservoirs. Each pulse adds heat. Each pulse adds volume. Each pulse carries dissolved gases. Imagine filling a vast underground chamber one ladle at a time. Not minutes apart, but centuries apart. The chamber beneath a supervolcano is not an empty balloon waiting to burst. It is a complex mixture of molten pockets intertwined with solid crystals. A dynamic system where parts melt, parts cool, and parts shift between states. Yet even in this mixture, pressure exists. The weight of kilometers of rock presses downward from above. Inside the magma, gases remain dissolved under that immense weight, much like carbon dioxide dissolved in a sealed bottle of sparkling water. Under pressure, everything appears calm. But as new magma enters the chamber, something subtle changes. Heat rises slightly. Surrounding rock warms. Crystals within the chamber may partially melt, increasing the proportion of liquid. Dissolved gases begin to concentrate within the melt. And gases are patient until they are not. As long as pressure remains high, gases stay dissolved. But if magma shifts upward even slightly, if fractures open and pressure drops, tiny bubbles begin to form. You imagine those bubbles as whispers within the molten rock. At first, they are microscopic, invisible. But each one expands as pressure decreases. Expansion increases internal stress. The magma becomes more buoyant, more mobile. Yet the surrounding rock resists. The crust above a magma chamber is strong. It bends slightly under stress. It fractures in small ways that may seal themselves with minerals. It accommodates change gradually. This is why supervolcanoes can remain in a state of partial melt for hundreds of thousands of years without erupting. The system adjusts. Pressure builds, then redistributes. Small earthquakes relieve localized stress. Hydrothermal systems release heat and some gas to the surface. Minor intrusions of magma stall and crystallize before reaching shallow levels. It is not a ticking clock. It is a breathing system. You begin to feel the rhythm of it. Magma accumulates. Rock flexes. Gas dissolves. Gas exhales, separating into bubbles. Pressure rises. Then perhaps a fracture opens, releasing a portion of that pressure into surrounding rock layers. A small earthquake trembles. The system settles again. Waiting. Patience is built into geology. The timescales are so vast that what feels like suspense to a human mind is simply processed to the planet. Thousands of years pass as easily as a single night. Under Yellowstone, scientists have identified multiple magma reservoirs at different depths. A deeper reservoir feeds a shallower one. Heat transfers upward gradually. Much of the magma remains crystal-rich, more solid than liquid. For a supereruption to occur, a large portion of that material would need to remelt into a more eruptible state. That requires additional heat input, sustained over long periods. And so, the chamber waits. You imagine it not as something restless, but as something suspended between states. Like water held just below boiling. Warm. Energetic. But not yet transformed into steam. Pressure is energy confined. It does not scream. It accumulates. The crust above responds elastically at first. Rock can bend slightly without breaking. But over time, if pressure continues to rise, brittle fractures may form. These fractures can connect, creating pathways for magma to ascend. Yet even then, ascent is not guaranteed to lead to eruption. Magma can stall in the crust, cool, crystallize, and become solid rock once more. Many intrusions never reach the surface. This is important to remember. Most magma does not erupt. Most pressure does not culminate in catastrophe. It is managed by the system itself through countless small adjustments. You imagine the Earth holding its breath. Not in panic, but in balance. Gas bubbles expand within magma when pressure decreases. If enough bubbles form and connect, they can dramatically increase the internal pressure of the chamber. But if pressure remains high, the bubbles remain small and contained. Containment is strength. The roof of the magma chamber continues to bear the load. Overlying rock weighs down like a heavy blanket, preventing premature release. Time stretches. Centuries drift by. Forests grow and burn and grow again. Ice ages come and go. Below, the magma system evolves incrementally. This waiting is not passive. It is active equilibrium. Heat moves through surrounding rock by conduction. Fluids circulate. Crystals grow and settle. Chemical compositions shift as different minerals form and separate from the melt. It is a slow alchemy. And through it all, pressure remains a partner to patience. You may feel a quiet resonance here. In your own life, pressure often feels urgent. But in the Earth, pressure unfolds across vast scales. It teaches you that accumulation does not demand immediate release. Systems can adapt. They can redistribute energy. They can stabilize. Only in rare circumstances does the balance tip decisively. And even then, signals usually precede transformation. Increasing seismic activity. Noticeable uplift. Changes in gas emissions. The Earth speaks before it acts. For now, beneath Yellowstone and other supervolcanic systems, the magma waits. Not dormant, but dynamic. Not frozen, but balanced. You rest above a planet capable of immense power, yet most of that power is held in quiet suspension. Pressure and patience coexist. And in that coexistence, the story moves toward a moment when containment might fail, not in explosion alone, but in something perhaps even more profound, when the ground itself no longer holds, and the Earth falls inward. You have imagined pressure building. You have felt magma gathering in darkness. Now, gently, you consider what happens when the balance can no longer hold. When people think of eruptions, they often imagine something thrusting upward: lava fountains, ash columns, fire reaching for the sky. And sometimes that is true. But a supereruption tells a different story. It begins deep below, in the magma chamber that has waited for millennia. Heat has accumulated. Gas has concentrated. Melt has become mobile enough to erupt. Fractures connect upward through the crust like fine cracks in glass. At a certain threshold, pressure exceeds strength. Magma surges upward through those fractures. As it rises, pressure drops. Gas dissolved within the melt separates violently into expanding bubbles. The magma fragments into tiny shards of volcanic glass and crystals. What was liquid becomes ash. The eruption column rises high into the atmosphere, sometimes tens of kilometers upward, carrying ash, pumice, and gas into the stratosphere. It is a release not of a small vent, but of an entire chamber's stored energy. But this upward violence has a consequence below. As vast volumes of magma are expelled, the chamber empties. Imagine removing the filling from beneath a roof. The ceiling remains only as long as the support below it remains. When too much material leaves too quickly, the overlying rock can no longer stand. And so, instead of only rising upward, the earth begins to fall inward. The roof collapses. Not in a single dramatic plunge, but often in stages. Ring-shaped fractures form around the chamber's edges. Blocks of crust subside downward into the space once occupied by magma. The surface sinks. This is how a caldera forms. The word caldera comes from the Spanish word for cauldron, and it fits. The result is not a pointed mountain, but a vast, basin-like depression, sometimes tens of kilometers wide. You imagine the ground lowering beneath your feet, not by inches, but by hundreds of meters in places. Forests drop. Rivers change course. Entire landscapes transform in a matter of days or weeks during the eruption. And then, eventually, the eruption slows. Ash settles. The eruption column weakens. The newly formed caldera lies quiet. Silence follows immensity. This is one of the most remarkable truths about supervolcanoes: the eruption is temporary. The caldera endures. At Yellowstone, the great eruption 640,000 years ago formed the caldera you stand in today. The collapse was not the end of activity, but it reshaped the region entirely. Lava flows later filled parts of the depression. Lakes formed. Hydrothermal systems emerged where heat still lingered close to the surface. Collapse becomes foundation. You begin to sense that destruction and creation are intertwined. The collapse of the roof does not mean the planet is broken. It means the internal structure has reorganized. Pressure that built for hundreds of thousands of years has been released. The chamber is partially emptied. The system resets into a new configuration. Calderas exist in other parts of the world too. Lake Toba in Indonesia fills a caldera formed by a supereruption about 74,000 years ago. The lake now rests where an enormous chamber once collapsed inward. What appears serene and blue from above was once the site of one of the largest eruptions in Earth's recent history. You let that idea settle gently. Beauty can grow from collapse. Even during collapse, the process follows physical laws: gravity pulling rock downward, fractures guiding movement, magma withdrawing through vents and fissures. There is no chaos without pattern. There is no violence without structure. You imagine standing at the edge of a caldera long after eruption has ceased. The air is still. The sky is open. Perhaps a lake rests in the center. Perhaps forests cover the slopes. You would not see the collapse in motion. you would see its memory. The Earth carries its history and shape. And beneath some calderas, magma systems persist. After collapse, new magma can intrude into the crust. Smaller eruptions may occur within the caldera over thousands of years. The system continues, though often in quieter ways. Collapse is not an ending. It is a transition. You feel the gentleness of that idea. When pressure can no longer be contained, release occurs. When support is removed, descent follows. But after descent, stillness returns. Rebalancing happens. Supereruptions are rare, separated by immense spans of time. Calderas formed by them remain as vast reminders of Earth's internal heat and capacity for change. And yet, even in these places, life persists. Grasses grow on caldera floors. Hot springs shimmer with microbial color. Birds nest along crater rims. The Earth integrates its own upheavals. You sense that collapse, though dramatic, is part of a broader rhythm. Pressure builds. Release happens. Land reshapes. Quiet returns. And high above the caldera, ash once carried into the sky begins its own journey, drifting across continents, altering sunlight, softening temperatures, reminding you that what rises from the Earth can reach far beyond its birthplace. You look upward now. The caldera has formed. The chamber has emptied. The ground has fallen inward. But the story does not end at the surface. It continues in the sky. During a supereruption, ash does not simply drift a short distance and settle quietly. The force of the eruption column can carry fine particles and gases high into the stratosphere, more than 20 kilometers above the ground, into a layer of the atmosphere where weather rarely disturbs them. You imagine a towering column rising like a pillar of gray light, expanding at its summit into a vast umbrella-shaped cloud. Within it are fragments of shattered magma, volcanic ash, along with sulfur dioxide gas and other volcanic emissions. Ash is not soft like fireplace soot. It is made of tiny shards of volcanic glass and mineral fragments, sharp at microscopic scales. When suspended in the air, these particles scatter sunlight. The larger ash particles fall out of the atmosphere relatively quickly, days to weeks, blanketing nearby regions in thick layers. But the finest particles, and especially the sulfur dioxide gas, can travel much farther. Sulfur dioxide, once in the stratosphere, reacts with water vapor to form tiny droplets of sulfuric acid. These droplets create what scientists call sulfate aerosols, microscopic reflective particles that can remain suspended for months or even years. And these particles change the sky. You imagine sunlight passing through a veil of fine mist. Some of the light is reflected back into space. Less solar energy reaches the surface. The planet cools slightly. This effect is called volcanic forcing. It is not permanent, but it is measurable. After the 1991 eruption of Mount Pinatubo in the Philippines, a much smaller event than a supereruption, global temperatures dropped by about half a degree Celsius for a year or two. The sulfate aerosols in the stratosphere reflected enough sunlight to cool the planet temporarily. Now imagine an eruption many times larger. Supereruptions can inject enormous quantities of sulfur dioxide into the upper atmosphere. The resulting aerosol cloud can encircle the globe, reducing sunlight for extended periods. Temperatures may decline noticeably. Growing seasons may shorten. Rainfall patterns may shift. This is sometimes described as a volcanic winter. You let the phrase rest softly. It does not mean endless darkness. It does not mean permanent ice. It means a temporary cooling, a climatic ripple spreading outward from a geological event. In Earth's past, large eruptions have coincided with periods of cooling. Ice cores extracted from Antarctica and Greenland preserve tiny traces of sulfate layers corresponding to ancient volcanic events. These layers are like faint fingerprints in frozen time. Sediment cores from lakes and oceans also hold evidence, thin ash layers marking distant eruptions, chemical changes indicating altered climate. The planet remembers. But it also adapts. Cooling from volcanic aerosols typically lasts a few years to perhaps a decade after very large eruptions. Eventually, gravity and atmospheric circulation remove the particles. Sunlight returns to previous levels. Temperatures recover. The climate system, like the geological system, seeks balance. Still, during that temporary cooling, ecosystems respond. Plants may experience shorter growing seasons. Some regions may become drier or wetter depending on how atmospheric circulation shifts. Ocean temperatures may change slightly at the surface. You begin to feel how interconnected the systems are. A chamber empties beneath the crust. Ash rises into the sky. Sunlight softens. Temperatures shift. Rivers, forests, oceans all respond. The Earth is not a collection of isolated parts. It is a network of relationships. Even the oceans feel the breath of a volcano. Volcanic ash settling into seawater can deliver nutrients like iron, stimulating blooms of phytoplankton, microscopic marine plants that form the base of ocean food webs. In this way, ash can both cool the climate and fertilize the sea. Destruction and nourishment intertwine again. You imagine standing beneath a sky dimmed slightly by distant aerosols. The sunsets might glow more vividly, scattering red and orange light through the fine particles. Historical accounts after major eruptions often describe unusually colorful sunsets. The sky becomes an artist's canvas, painted by volcanic dust. But you also remember that supereruptions are rare. The last known supereruption at Yellowstone occurred 640,000 years ago. Lake Toba's massive eruption happened around 74,000 years ago. These events are separated by vast spans of time. Human civilization has not experienced a supereruption in recorded history. This perspective brings calm. The climate system today is influenced by many factors: solar variation, ocean circulation, greenhouse gases. Volcanic forcing is one piece of a complex puzzle. When it occurs, it leaves a temporary imprint, then fades. Ash eventually settles. Sulfate aerosols fall out of the stratosphere. Sunlight strengthens again. The atmosphere clears. And life continues. You realize something important here: even immense geological events do not permanently overpower the climate system. They perturb it. They shift it temporarily. But the planet possesses feedback mechanisms: ocean heat storage, atmospheric circulation, biological processes that help restore equilibrium. This does not make supereruptions trivial. Their regional impacts would be profound. Thick ash deposits could disrupt agriculture and infrastructure near the source. Air travel would halt across affected regions. Ecosystems would need to adjust. But globally, the cooling would not be endless. The Earth has endured such events before. Ice ages have come and gone. Asteroids have struck. Supercontinents have formed and broken apart. Through it all, the climate system has oscillated, recovered, transformed. You feel a quiet reassurance in that resilience. Ash in the sky is a reminder that the planet breathes in layers. A breath from deep within can reach the upper atmosphere. A shift underground can ripple through clouds and oceans. And yet, after the breath, comes stillness. The aerosols thin. The sky brightens. The temperature steadies. In the long arc of geological time, even super-eruptions are moments, dramatic, yes, but not eternal. You look upward one last time in your imagination. The ash cloud disperses. Sunlight filters through once more. The world continues, altered but alive. And somewhere on the ground below, scientists watch instruments carefully, studying tremors and gas emissions, learning to listen for the subtle signals that precede such immense breaths, listening not for panic, but for understanding, as the story turns gently toward those who keep watch over the unseen. You descend now, not into magma or molten rock, but into understanding. The ground beneath Yellowstone or any supervolcano is alive with motion. Yet it is quiet to human ears. A tremor too small to feel occurs every few minutes. Rocks shift imperceptibly. Gas escapes in tiny quantities. The system speaks in whispers, not shouts. Scientists are the listeners. You imagine walking alongside them in a wide field dotted with instruments. Seismometers stand like small, silent sentinels, recording vibrations from deep within the earth. Some tremors are barely perceptible, far below the threshold of what you could feel even if you tried. But the devices detect them, translating subtle vibrations into signals that reveal patterns of movement. You feel the rhythm of these tiny quakes as though they were heartbeats, the Earth's slow pulse. Each one tells a story. A fracture adjusting. A block of rock yielding under pressure. A magma pocket settling. Alone, each event seems insignificant. Together, they form a narrative spanning decades, centuries, or millennia. Satellites orbit silently above, scanning the surface. They measure uplift, detecting changes in the elevation of the land by mere centimeters. You imagine looking down at a broad plain and noticing that over a few years, it has risen a few centimeters here, fallen slightly there. It is imperceptible to your eyes, yet these measurements reveal the breathing of a colossal system beneath. Ground deformation is like the Earth exhaling and inhaling. Expansion occurs where magma intrudes, swelling the crust. Contraction occurs where pressure subsides. These motions can be sudden or gradual. Sometimes they continue for decades, always subtle, always patient. And then there are gas sensors. You kneel beside one, imagining its tiny internals analyzing the air above a fumarole. Sulfur dioxide rises as vapor, invisible but detectable. Carbon dioxide escapes too. Radon gas seeps from cracks. Their concentrations can hint at processes deep underground. Perhaps magma has shifted slightly. Perhaps new pathways have opened for gas escape. Each measurement is a word. Each pattern, a sentence. Scientists are translating the language of the Earth. They combine data from many sources: seismic vibrations, satellite imagery, ground deformation, gas emissions, and even subtle changes in temperature. Together, these measurements form a multi-dimensional map of an otherwise unseen world. Technology becomes a stethoscope on the Earth's chest. It listens to rhythms that are too faint or slow for human senses. You imagine the planet lying beneath, not as passive stone, but as a living system, responsive to internal pressures, heat, and chemical reactions. The magma chambers beneath Yellowstone are complex. They are not empty caverns but a mix of solid crystals, partially molten rock, and fluid melt. Some regions are hotter, others cooler. Some pockets contain more gas. Their behavior cannot be predicted by a single observation. Only through careful, sustained monitoring can scientists begin to understand the dynamics. You see them charting earthquake swarms. Hundreds of tiny tremors, clustered in space and time. Patterns emerge. Magma may be moving, but not all movement leads to eruption. Small pulses, minor adjustments, repeated processes, they tell a story of ongoing equilibrium. Imagine looking at a screen showing the ground rising a few centimeters over months, then falling slightly. You might think it insignificant, but these subtle motions represent the slow release and accumulation of energy. The planet is communicating, and humans are learning its grammar. Hydrothermal systems also speak. Geysers erupt with regularity. Hot springs change in flow or color. Even minor variations are signals of what lies beneath. Scientists observe the timing, chemistry, and temperature of these features, integrating the information into their models. Sometimes satellites detect heat anomalies. Remote sensors pick up changes in vegetation patterns caused by subtle shifts in ground temperature. Everything is connected: the magma below, the crust above, the living ecosystem on the surface. Listening requires patience. Data is collected over decades. Tremor patterns are compared over years. A single measurement is never definitive. Only long-term observation can reveal the true behavior of these vast systems. You imagine a scientist looking at decades of data and noticing that uplift has slowed after a period of acceleration, or that gas emissions have increased slightly over months. Each observation is part of a conversation with the Earth, slow, careful, and ongoing. And yet, even as scientists monitor and model, the Earth retains mystery. Not every movement is fully understood. Magma may shift unpredictably in small regions. Gas may accumulate in unexpected pockets. Fractures may form in ways no one anticipated. This does not breed fear. It breeds respect. Respect for timescales that exceed human perception. Respect for forces that operate below senses. Respect for a system so vast and intricate that even centuries of observation can capture only fragments of its behavior. You begin to appreciate the humility in science. The Earth does not yield its secrets easily. But with persistent listening, we learn to read its subtle cues. Patterns emerge. Probabilities are calculated. Risk is understood, not eliminated, but managed. The scientists you imagine are calm. Their curiosity tempered with care. They are not watching for panic but for understanding. The stakes are real, but the focus is knowledge. Imagine yourself walking among them. Feeling the vibrations, watching the instruments, observing the land. You sense a profound connection, the human mind reaching out to understand the planet's quiet, patient rhythms. Even now, beneath your feet, magma moves imperceptibly. Gas bubbles form and collapse. Rock bends under pressure. Tremors ripple through kilometers of crust. Uplift and subsidence continue in slow cadence. Heat migrates from deep within the mantle. Minerals slowly crystallize and melt. All of this is happening unnoticed by most of the living world. You are in a unique place of awareness, attuned to whispers the Earth sends to those who listen carefully. The Earth teaches a lesson about vigilance without alarm, observation without interference. Watching the unseen requires stillness, patience, and trust that patterns exist even when they unfold beyond human perception. You understand now that eruptions are not surprises in the chaotic sense. They are outcomes of processes that can be monitored, modeled, and anticipated, not predicted with absolute certainty, but approached with a rhythm of knowledge. And so, beneath Yellowstone, scientists continue their work. They gather data, test hypotheses, and refine models. Their instruments hum quietly. Satellites orbit endlessly. Gas analyzers sample minute emissions. Seismic stations register tiny tremors. The planet speaks. Humans listen. And you, standing in imagination, sense the elegance of it all. Pressure gathers below, magma shifts, and yet there is balance. Patterns repeat. Processes persist. The earth is patient. And humans are learning the language of its hidden heart. Even as you contemplate this, your mind drifts toward timescales longer than centuries. Layers of ash from past eruptions remain in sediment and rock, holding records of magma behavior, eruption volumes, and environmental effects. The past and present intertwine through careful observation. Listening is understanding. Understanding is calm. Calm is the way we meet the Earth's immense, hidden processes, not with panic, but with attentive presence. And as you prepare to move your attention toward the deep past, to the ancient eruptions that left their mark across continents, you carry with you this sense of connection. The unseen can be observed. The unknown can be approached with patience. And beneath all, the Earth continues its slow, whispering conversation, waiting for those who choose to listen. Now, gently, you drift backward through time. You are no longer in the present valley, no longer beside steaming geysers or carefully calibrated instruments. Instead, you move through layers of history, strata built up over hundreds of thousands of years. Imagine stepping into a slow, endless corridor, where each floor is a moment of Earth's memory, each wall a record of heat, pressure, and eruption. The first layer beneath your feet is soil and sediment deposited in the last few centuries. Beneath that, thicker layers of ash and pumice hint at older volcanic activity. Some of it is from minor eruptions, the kind that shape local landscapes. Others are markers of supereruptions, catastrophic events that blanketed continents and shifted climates. You imagine geologists, patient interpreters of time, slowly digging, coring, and reading these layers. They treat each stratum as a page in a book written by the Earth itself. No words, no sentences, only material, texture, and composition, telling stories in a language of mineral, crystal, and gas. One layer of ash might be hundreds of meters thick near the eruption site, thinning gradually as you move farther away. Each particle, microscopic or larger, is a relic of a moment when the planet exhaled an extraordinary amount of energy. You see it not as destruction, but as a preserved moment in a slow, ongoing process. You trace the layers outward, across continents. Tephra from a supereruption spreads far and wide. Wind carries ash across oceans. Rain deposits it into lakes. Soil and vegetation slowly cover it, but the layer persists, waiting for someone to notice it. These layers are not uniform. They reveal subtle differences in chemical composition, in crystal structure, in color. Each variation tells a story, a change in magma chemistry, a difference in eruption style, a shift in climate. It is as if the planet, in its patience, has left a nuanced diary. You imagine yourself flipping through these pages with gentle fingers. One layer tells of rapid uplift and pressure release. Another whispers of slower intrusions that never reached the surface. Together, they create a timeline of Earth's internal rhythm. And within this memory, you perceive the cycles of pressure, patience, and release. Supereruptions are rare, separated by hundreds of thousands of years. Yet their effects ripple forward, shaping landscapes, soils, and ecosystems. Forests regrow on layers of ash. Rivers carve new channels through hardened pumice. Life adapts. Time itself feels slow. Human lifetimes are fleeting. Civilizations are transient. But these layers endure. They witness epochs of change. They record the patient, persistent work of geological forces. The past supereruptions teach about scale. Energy accumulated over millennia is released in hours or days. Entire regions are blanketed in ash. Atmospheres are altered. Climates shift temporarily. Yet eventually, life returns. Rivers flow again. Plants recolonize. Animals migrate back. The earth heals, integrates, and evolves. You realize that studying these layers is a form of listening across time. Scientists extract cores from lakes, dig trenches through caldera deposits, and analyze mineral compositions to reconstruct events that occurred long before humans existed. Each layer is a sentence, each mineral a word, each isotope a punctuation mark. The Earth is patient, yes, but also precise. Its memory is vast, storing not just evidence of eruption but subtle indications of environmental impact. Oxygen isotopes reveal climate shifts. Ash thickness maps hint at wind direction. Carbon content in soil shows ecological response. You feel a profound sense of connection. By reading these layers, you connect to events far older than your own experience, to processes that shaped continents, climates, and life itself. You sense that the same principles guiding magma beneath Yellowstone today also applied hundreds of thousands of years ago: pressure accumulation, chamber formation, eruption, collapse, and renewal. This perspective is both calming and humbling. The Earth operates on timescales far beyond your immediate perception. A supereruption that shaped a landscape long before humans walked the continents now rests quietly beneath soil and forest. Its memory persists, influencing topography, ecosystems, and climate patterns subtly, over centuries and millennia. You imagine the cycle repeating. Magma gathers. Pressure builds. Fractures form. Eruption occurs. Collapse reshapes the land. Life returns. Ash spreads. Climate adjusts. Then, again, the system rests. And through each cycle, the planet writes its history in rock and sediment. In this deep time perspective, you notice the continuity of process. Today's earthquakes, minor uplifts, and hydrothermal features are not anomalies but part of a continuum. They are connected to the events recorded in the ash layers, threads in a tapestry stretching over hundreds of thousands of years. You can almost feel the slow heartbeat of the Earth, its pulse measured not in seconds or minutes, but in millennia. Each layer is a mark of that pulse, a gentle, persistent record of energy, movement, and adaptation. The memory held in these rocks is not inert. It is active knowledge. Geologists and volcanologists interpret it to understand probabilities, not certainties. They read the past to anticipate the long-term behavior of supervolcanoes. Ancient eruptions provide context for modern observations, showing what magnitude of change is possible and what remains unlikely. And yet, the Earth keeps its ultimate decisions to itself. Even with thousands of years of record, precise timing of the next supereruption cannot be known. What is knowable is the pattern, the rhythm, and the fact that the planet operates through patience and pressure, persistence and adaptation. You feel this lesson deeply. Time is vast. Energy accumulates slowly. Release can be dramatic. And afterward, life, land, and climate adapt and continue. You are part of this ongoing rhythm, a quiet observer of a much larger story. Looking down at the layered deposits, you see connections. The ash that drifted across a continent in the past influences soils today. Layers of pumice form natural aquifers. Minerals released from ancient eruptions feed ecosystems in subtle ways. Even when eruptions are catastrophic locally, their impact on the planet is woven into a larger pattern of continuity and resilience. You take a slow breath. Consider the patience, the scale, the interplay of pressure and release. Consider that the Earth has witnessed these processes countless times, and yet each eruption is unique, shaped by variables no one can completely control. Deep time teaches perspective. What seems sudden to human eyes is often slow and deliberate from the Earth's vantage. Patterns emerge only over centuries, millennia, eons. The planet reminds you that observation, patience, and understanding are vital companions to curiosity. And in this vast memory, there is a quiet reassurance. Even immense events that once reshaped landscapes do not define the entirety of Earth's story. The planet absorbs, integrates, and continues. Life persists. Systems adjust. Energy disperses. Balance returns. You rise from the layers, gently returning to the present. Yet the echoes of deep time linger. You carry with you the knowledge that beneath your feet, processes continue, slow and patient. The memory of eruptions past informs the behavior of today. Pressure accumulates, heat migrates, and the cycle continues, quietly, persistently, across epochs beyond your immediate perception. And as you look toward the present again, you realize that the story of supervolcanoes is not only about catastrophic events. It is a meditation on time, energy, resilience, and the quiet persistence of a planet that remembers every eruption, every collapse, every breath it has ever taken. You rise from the deep past, back into the present. The landscapes of Yellowstone stretch before you again. Steam rises from geysers. Rivers flow. Bison graze. Time seems ordinary, familiar, calm. Yet you carry the weight of what you have seen, the immense eruptions of the past, the slow accumulation of pressure beneath the surface, the collapse of calderas, the ash that drifted across continents. It is natural to feel a flicker of unease. The idea that the Earth could release such power beneath your feet is unsettling. Your mind imagines catastrophic scenarios, skies darkened with ash, temperatures cooling, cities covered, lives disrupted. But now, you breathe. Slowly. Deeply. And you let science guide your thoughts. Science does not deal in panic. It deals in observation, measurement, and probability. It is not alarmist. It is deliberate. It observes the past to understand the present, models the present to anticipate the future, and acknowledges uncertainty without letting it dominate thought. You remind yourself that supereruptions are extraordinarily rare. Yellowstone's last supereruption occurred 640,000 years ago. The one before that, over 1 million years earlier. The probability of such an event in any given human lifetime is extremely low. Most people will live their entire lives without witnessing anything even close to a supereruption. Even the smaller eruptions, though more frequent, are minor compared to the immense scale of a supereruption. Lava flows, hydrothermal explosions, minor ashfalls, these are localized. They affect immediate areas, but they do not reset continents or reshape climate for decades. Scientists maintain vigilance because understanding patterns reduces risk. Seismic networks, gas sensors, GPS measurements, and satellite imagery are tools that translate subtle shifts in Earth's internal systems into information we can comprehend. They reveal early signals that allow for preparation and planning, not panic. You imagine a scientist reviewing the data quietly. Tremors are normal. Uplift is measured in centimeters. Gas levels fluctuate within expected ranges. Nothing indicates an imminent supereruption. The Earth, for now, is balanced. Probability is a gentle companion. It does not eliminate uncertainty, but it frames it in a way that can be held calmly. You realize that fear often comes from imagining certainty in the face of unknowns. Probability allows for the unknown to exist without overwhelming you. You picture probabilities as a spectrum of outcomes. On one end is the highly unlikely, extreme scenario. On the other, everyday normalcy. Most life occurs comfortably in the middle. Even within extreme events, understanding what is possible allows for preparation and peace of mind. The Earth has operated on timescales far beyond human comprehension. Supervolcanoes follow rhythms measured in hundreds of thousands of years. Geologic time is vast. Human lifespans are brief. By this measure, what feels urgent or threatening is usually gentle in the broader scheme. You feel the relief of perspective settling around you. The probabilities of tomorrow do not demand fear. They demand observation, patience, and understanding. They invite you to marvel at the slow, persistent workings of the planet rather than fixate on unlikely catastrophe. Yet, uncertainty remains. That is part of life. Even when probabilities are small, the outcome is not zero. The unknown is real. And that is not meant to alarm, it is meant to deepen curiosity, respect, and attentiveness. You realize that monitoring continues, not to provoke worry, but to maintain connection. Seismometers hum. Satellites orbit. Gas sensors sample. Patterns are analyzed, trends are followed, models are refined. Each measurement reinforces understanding, allowing humans to coexist safely with systems far larger and more powerful than themselves. Probability and preparation walk hand in hand. Awareness replaces fear. Knowledge replaces imagination of catastrophe. You feel calm knowing that every movement of magma, every tremor, every subtle uplift is being observed and interpreted. Even if something were to change suddenly, warning systems and scientific understanding would provide time for response. Humans have learned to anticipate, adapt, and act in ways the planet itself does not. You are part of this ongoing dialogue between Earth's internal rhythms and human observation. You allow your mind to settle on this balance. Magnitude and rarity coexist. Power and patience coexist. The Earth carries immense energy, yet that energy is contained within predictable patterns of pressure, crystallization, and movement. And you carry your own calm. Probability becomes a tool to hold uncertainty gently, rather than a source of panic. You understand that most life unfolds between extreme events, quietly, normally, beautifully. Seasons continue. Rivers flow. Forests grow. Life adapts. You feel gratitude for the patient work of observation scientists, geologists, volcanologists who translate the subtle movements of the Earth into knowledge. They watch the unseen, interpret the slow rhythms, and allow us to live with awareness rather than fear. Standing once more in Yellowstone, you sense continuity. Past eruptions are recorded in ash layers. Present tremors are measured and understood. The future exists in probabilities, in gentle rhythms, in the slow accumulation of pressure that may or may not lead to eruption. The world is immense, and yet understanding its processes provides peace. You sense the steady pulse of the Earth beneath your feet, vast and deep, filled with energy and movement. You also sense the human capacity to observe, to learn, to integrate this knowledge into life without panic. Time stretches again. Probabilities are not absolute predictions. They are guidance, a framework to live comfortably within the scale of the Earth's processes. They are reassurance that the planet's immense power can be respected, understood, and peacefully observed. And as you reflect on probabilities, your mind drifts naturally toward the intimate connection between humans and Earth, how you are part of a system that waits, breathes, and continues across centuries, millennia, and epochs. You sense that the next step in this meditation is not the unseen forces alone, but your own place upon this living, breathing planet. And so, You feel the quiet invitation to settle back onto the ground, to sense your body in harmony with the rhythms beneath, as the earth continues its slow and patient journey through time. You return to the present moment, to the ground beneath your feet, to the familiar sway of trees and the whisper of wind. The earth is quiet here, at least to your senses. Yet beneath the calm surface, the planet continues its invisible work. Heat rises from the mantle. Magma flows slowly in chambers deep underground. Pressure builds, shifts, and releases, a rhythm older than any memory you carry. You settle down onto the soft earth. Feel its weight, its texture, its steady presence. Imagine the crust beneath you as a living fabric, flexible yet strong, carrying immense forces with silent patience. You are resting atop a dynamic system, a body that breathes slowly, its heartbeat measured in millennia rather than seconds. The rocks you touch were formed in fires of ancient eruptions, reshaped by glaciers, sculpted by rivers. Each pebble, each grain of sand is a fragment of Earth's long memory. Some have traveled thousands of miles, carried by rivers or glaciers. Others lie in place, witnesses to events that occurred before humans walked the land. You are held by this vast accumulation of history, by a planet that remembers every eruption, every collapse, every pulse of heat. The air smells of pine and mineral. Steam rises from hot springs nearby, small reminders of the heat moving far beneath. Tiny tremors occur constantly, mostly unnoticed, except by the instruments that watch patiently. You do not fear them, you feel the cadence of the earth's breath, slow and deliberate. You consider pressure again. Beneath Yellowstone, and beneath many other landscapes, magma waits, moves, and exerts its silent force. Rocks bend imperceptibly. Gas is dissolved and released in tiny amounts. The system manages itself, holding vast energy in balance. You, resting above, are connected to this process. Your presence is part of the Earth's ongoing story, intertwined with rhythms too deep for human perception. Life flourishes because of this planet. Rivers flow, shaping valleys and transporting minerals. Soil builds, nurturing seeds. Trees grow, forests thrive, animals roam. Even the energy stored and released in supervolcanoes contributes to life's continuity. The nutrients scattered by ash enrich ecosystems. The geological processes you have traced are part of the same system that allows grass to grow beneath your feet, insects to hum, and birds to glide overhead. You imagine the deep layers beneath your resting place. Kilometers of rock, slowly deforming, flexing under pressure. Magma chambers, partially molten, awaiting the rare moment when containment will fail. Fractures adjusting, hydrothermal fluids circulating, mineral crystals slowly forming and dissolving. All of it happening quietly, patiently, without urgency. In this vastness, your own breath aligns naturally with the planet's rhythms. Slow. Steady. Continuous. You are both observer and participant. The Earth does not merely hold you, it moves with you, responds to your weight, to the ecosystems you inhabit, to the history you inherit. You reflect on time, human time and geological time. Millennia pass below in motions you cannot see. A supereruption may come in hundreds of thousands of years, or not at all in your lifetime. Life continues in cycles of growth, decay, and renewal. In this perspective, the worries of daily existence shrink. The Earth's vast patience is a balm. You notice the continuity. Past eruptions, pressure accumulations, collapses, ash dispersals, all are part of the ongoing narrative. They are not distant, abstract events, they are threads woven into the fabric of your present, shaping the land, influencing climate, nurturing life. You, resting here, are part of that thread. Your body, your awareness, your curiosity all exist within the context of the planet's living processes. You sense the quiet intelligence in these slow movements. The Earth holds energy and releases it with perfect timing, according to natural laws. It adapts to change, absorbs stress, heals from rupture. Mountains rise. Valleys form. Rivers cut channels. Forests regrow. Even when enormous forces move beneath, life finds equilibrium. This awareness brings a gentle humility. You are not separate from the planet. You are a participant in its story. The ground beneath you is more than solid rock, it is living history, energy, and possibility. You feel gratitude for its support, its endurance, and its quiet work. You imagine all the systems continuing silently tonight. Magma moving slowly. Water cycling through rivers, lakes, and clouds. Wind brushing over ridges. Stars spinning above in their vast, steady arcs. The Earth's breathing is continuous. Your own breathing harmonizes with it. You are part of a living, breathing planet, held in balance by forces both immense and gentle. Even as you drift towards sleep, you carry this awareness that the energy beneath your feet, the pressures and releases, the long cycles of eruption and calm, all of it is ongoing. The planet is patient. It is resilient. It is constant. You rest on it, moved by it, held by it. And as your eyelids grow heavy, you feel a connection across scales of time, space, and life. You are the observer of a story billions of years in the making. You are resting atop a system of extraordinary power and delicate balance. You are alive within a planet that endures, that breathes, that nurtures. The heat still moves below. The pressure still gathers. Magma waits. Rock bends. Water flows. Gas rises. Life persists. And you, resting quietly, are a part of it all. In the gentle rhythm of this realization, sleep arrives. Your mind relaxes. Your body releases tension. You feel held, not just by the ground beneath, but by the entire living, breathing planet. And as dreams begin, you carry with you the quiet knowledge that the Earth continues its work, patient, powerful, and eternal, beneath your dreams, beneath your presence, and beneath all the moments that stretch forward into tomorrow. You are cradled by a planet that holds you, and its breath moves gently, slowly, patiently, onward, as you drift into rest.